Let us now see an example, or in fact 3 examples on how we can understand the Clark and Parkes transformation in a better way, and how we can visualize the transformations. So, I have taken 3 examples here, one with a balanced voltage, one with an unbalanced voltages, 3 phase unbalanced voltage, and one with the balanced voltages with harmonics like fundamental 5th and 7th. So, these conditions are shown in these 3 figures, okay, and we will go through it one by one. Okay. So, let us first start with the balanced voltages and understand how we can interpret the Clark and Parkes transformation. So, let us take 3 waveforms. Okay. So, first example, this is for the balanced voltages. Okay. So, let us take 3 balanced voltages which are given by these equations V A, V B and V C. So, these are the 3 balanced set of voltages. So, how do you draw it? So, here in this one, this axis is the time axis, okay, and these are the 3 voltages V A, V B and V C, okay, given by this equation. Now, let us do the first the Clark's transformation on these 3 sets of voltages. So, we are trying to find out V alpha, V beta and V 0. Now, since the sum of these 3 voltages is equal to 0, the sum of V A, V B, V C as shown here, the sum is equal to 0, therefore, automatically implies that V 0 t will be equal to 0, because V 0 t is by definition 1/3 of V A t plus V B t plus V C t. Okay. So, this is 1/3 of V A t plus V B t plus V C t. Okay. And so, this is equal to 0 in this case. So, in this waveform we can see that the V 0 component is having a 0 magnitude. Okay. What about alpha and beta components? The alpha and beta components are or can be obtained from the matrix which we have calculated or shown before, and so we have seen this TC matrix, Clark's transformation matrix, and accordingly we can find out V alpha and V beta. V alpha and V beta have the same magnitude as the peak of the AC VA, VB and VC. Okay. So, this is magnitude invariant transformation. Okay. The magnitude remains the same, and you can also see that the V alpha, the phasor or the waveform V alpha is leading the waveform V beta, okay. And this is correct because I can just quickly draw it here, that V alpha should be leading, because you see we have said earlier that this is the alpha axis and this is the beta axis, and these are stationary axis. Okay. And then you have the space vector corresponding to this V A, V B, V C. This is a space vector which is rotating at a speed of omega. And so, as the space vector is rotating anti-clockwise direction, so at first it is crossing the alpha axis, so and then after 90 degrees it is crossing the beta axis. So, therefore, at first alpha is peaking. Okay. So, on the time, if I see the time domain, V alpha will first reach its peak when V r is crossing this portion. Okay. So, V alpha is peaking, and after that, after 90 degrees, when V r comes here, then it is V beta, means the beta axis projection is peaking, and so we see it here. Okay. So, in the time domain, alpha is 90 degrees leading to the beta waveform. Okay. So, this is the second about the alpha, beta and 0 components. What about the dq0 components? Okay. Now, we have the 0 is equal to the V0 in the alpha beta 0 transformation is 0. So, the in the dq0 transformation also this will be equal to 0. Okay. In fact, we have not shown the dq0 just for clarity. So, V0 is also 0 here. So, I can write it here, V0 is equal to 0 in the dq0 transformation. Now, in this example, we have made the dq axis to rotate at the same speed as the speed of the reference vector. So, if the reference vector is here, so I can now so the dq is rotating. So, the d, I will put the d axis here and I will put the q axis here, and they are also rotating at the same speed omega at which the VR vector is also rotating. Okay. This is the VR vector. The VR vector is rotating at omega, and the d and q axis, okay, the rotating reference axis, they are also rotating at the same omega. And furthermore, the d axis is aligned or coincident with the reference vector, okay, voltage space vector. It is aligned with the voltage space vector VR. So, if it is aligned with the voltage space vector, and if you are an observer standing on the d axis, what will you see? You will see that the magnitude of the space vector is always constant and it is maximum. So, this is what is shown here, V d is equal to 1, and it is always a constant straight line value. What about the observer who is standing on the q axis? What will he see? He will see that there is no projection on the q axis, and hence V q is equal to 0 in this case. Okay. So, if this was d dash and q dash, if I had placed the dq rotating axis at some other angle rotating again at omega, then I would have seen some projection of V q. Of course, there will be. So, if you can extend this V r, if you extend it, you will get, okay, some projection on the this one, and there will be some projection on the q dash axis. This is the d dash and q dash projection. So, if there was, if this d dash axis and q dash axis is not coincident with the reference vector or the space vector, then we would have seen a projection, okay, some projection on both d and q. So, then in that case this V q will not be equal to 0. What will happen if this d dash and q dash do not rotate at the same speed as omega? Okay. It can also happen that the reference vector does not rotate, sorry, the reference axis or the dq axis is not rotating at the same speed as the reference or the space vector, then we would have seen an AC quantity on Vd and Vq. We will talk about it in a few minutes time. Okay, in one of the next slides you will understand what is happening, but this is also a possibility. So, in this example we have shown how V alpha, V beta, V 0 will look like and how Vd and Vq look like. In this case we have taken the dq axis rotating at the same speed as the speed of the space vector, and we have also ensured that the d axis is coincident with the space vector. So, this was the first example. Okay. Let us now take the second example, and this example is about unbalanced voltages. Okay. Now, in case of unbalanced voltages, so we have taken an example here. So, VAT is 1.3 Vm sin omega t, Vb is Vm sin omega t minus pi by 3 and Vc is 0.5 Vm. So, we have only made the magnitudes different. Okay. So, now of course, we can immediately say that the sum of these three voltages is not equal to 0. Therefore, we will expect a 0 component in the alpha beta 0 transformation, and we can see it here now that V 0 has a it is non-zero in value, it has some magnitude. Okay. Now, how do you visualize this? Okay. As I have told you before, so let me if it is an unbalanced system, then as I have told you that we can visualize this as this alpha beta and 0, and we can visualize as if we have in this case we are inside a box, okay, and there is a space vector which is rotating 3 dimensionally inside the box. Okay, there is a space vector which is rotating inside this box. Okay, it is an ellipse. Okay, it is 3 dimensional, it is rotating, and so therefore, definitely it will have some projection on the alpha axis, beta axis as well as the 0 axis. Okay. And these projections are found out in the alpha, beta and 0 when we see it in the with respect to time. Okay. So, this is what is shown in this V alpha, V beta and V 0. Okay. Now, let us see the Vd and Vq components. Now, of course, let us first talk about the Vdq 0, V 0. V 0 is, as I told you, V 0 is an axis which is perpendicular to the rotating dq frame, and so it will also see, if we are making the d and q to be coincident in the same plane in which alpha beta plane is there, if these two planes are coincident, then 0 of the alpha beta 0 transformation, the 0 axis and the 0 axis of the dq 0 transformation, they will be coincident, and so we will see V 0 to be same. Okay. Now, what about the d and q? here we observe that the D has an average value and there is a second harmonic component, or in the D waveform there are two lobes. In the D waveform there are also two lobes in the Q waveform. Why are these lobes coming? So, that means there is a second harmonic component in the VD and VQ waveforms. Why are they coming? So, when we, how do you justify this? So, we had said that there was this okay. So, there was this vector, space vector rotating in the alpha beta 0 plane. Okay. So, if you look from the top, okay, you will see the alpha beta plane, and how will you see this? You will see the alpha plane here and beta plane here. Okay. 0 plane is perpendicular to the both of them. Now, there is a D, there is a rotating dq here. This D and Q is rotating at omega speed. So, what is happening? D is rotating, D and Q axis, they are rotating at omega speed, and alpha beta are stationary, and on this two stationary axis we have two variables which are oscillating. So, this alpha variable is oscillating on this V alpha is so, yeah, because this projection, the projection of this vector here on the alpha axis, with time you will see that it is oscillating on the alpha axis. Similarly, on the beta axis also there is one variable which is oscillating. Okay. So, let us take this alpha variable alone and then we will understand how the beta variable is working. So, let us, I will just remove this beta and we will concentrate on the alpha variable. So, here we see that, okay, here we see that this is the alpha variable which is rotating or oscillating on the alpha axis, and then there is a D axis which is rotating at omega speed. Now, if you remember from your single phase analysis or single phase induction motor analysis, there a pulsating magnetic field on a stationary axis, we can treat it as two rotating MMFs, but in opposite direction. So, one pulsating MMF on this axis can be treated as sum of two MMFs, one rotating like this and another one rotating like this, clockwise and anti-clockwise, okay, equal magnitude which rotates in two directions, one clockwise, one anti-clockwise, and this is the pulsating magnetic field. Okay. So, it all comes from the splitting of the sine wave. So, sin theta sin omega t is in the form of sin A plus B plus sin A minus B, from there it comes here. Okay. Yeah, you can do the mathematics and see. So, there are two magnetic fields which are rotating in opposite directions. So, this magnetic field here on the alpha axis, so this not magnetic field. So, this variable which is now rotating or oscillating on the alpha axis, we can also split it into two parts. Okay. So, one part is rotating with this way omega speed, and the other one is rotating anti-clockwise with omega speed. Okay. So, this green waveform which is oscillating, okay, the green one is now split into two parts, yellow one omega anti-clockwise and omega clockwise. So, if now you are an observer, okay, you are an observer standing on the d axis and you are also rotating by omega. So, how will you observe these two waveforms here, number 1 and number 2? How will you observe them? Of course, number 1 will be stationary with respect to you, because number 1, the first waveform, the first rotating waveform anti-clockwise is in synchronism with you. You are moving, the first one is also moving along with the same speed. There may be a phase difference between you. So, you will see a constant phase difference between you and the first waveform, but it will be a steady DC value. Okay. What about the second waveform? The second waveform you will see as something which is rotating at 2 times the speed, because you are moving at omega here, this second waveform is moving at omega speed in the other direction. Okay. So, therefore, you will see this second waveform as something which is a second harmonic. So, this will appear to you, this waveform or this waveform will appear to you as a second harmonic component. Okay. And this is what makes that dq0. If you see in the dq0, okay, we had, if you had the Vd, there was one average component and then there was a second harmonic. Okay. The average component comes from this waveform 1, that is this one. This gives the average one, because it is, you are seeing it as a constant value. Okay. The second harmonic component comes from waveform 2, which is rotating in the opposite direction. Okay. So, therefore, you will see a dq with a second harmonic component superimposed. So, this is the physical meaning of the waveform which you see here. Okay. The d has a second harmonic component, you can see here, this is 1 first cycle and then this is 2 cycles here. So, that is why we have said there is a 2 omega component along with a DC value. Okay. So, this is the physical meaning of what is happening. Now, let us take the third example. Suppose you have a balanced set of waveforms with harmonics, 5th, 7th harmonics. Okay. So, in this example, we have taken a balanced voltages with 1st, 5th and 7th harmonic components in VA, VB and VC. Okay. So, if it is a balanced waveform, the sum of these 3 quantities or sum of these 3 VA, VB, VC, the 3 waveforms is 0 at all instants of time. So, therefore, the 0 component is 0. So, V0 is 0, VA plus VB plus VC equal to 0 at all points of time. That is how we have taken this waveform. Now, of course, then you will understand that V0 is 0 both in alpha beta as well as in dq domain. Now, V alpha and V beta have have a nature which is similar to the previous one, but you can see there are harmonics. So, there is a harmonic. So, you can see this is a harmonics appearing. Okay. Now, there is something interesting here in the Vd and Vq domain. There is a 6th harmonic component which I have said it contains the 6th harmonic in Vd and Vq. Now, how come this 6th harmonic comes? How do you know that this is a sixth harmonic? You can start from here, say you are here it is 1, 2, it is almost here 3, 4, 5, 6. Okay. So, there is a sixth harmonic ripple or a sixth harmonic AC component present on Vd, and similarly it is also present on Vq. Okay. Where does this sixth harmonic come? So, in order to understand it, again we will analyze it. So, we can analyze how the sixth harmonic will come. So, okay. So, this is the d axis. Okay. Suppose we take only the d axis, the d axis is rotating at omega speed. Now, in this case I have added a fifth harmonic component with the Va, Vb, Vc. So, the fifth harmonic component is rotating at a 5 omega speed. Okay. But in this case we have chosen the fifth harmonic to be rotating in the reverse direction. So, the fifth harmonic component, okay, the fifth harmonic component. So, this is a small space vector. So, this is I will say V5. V5 is a space vector which is rotating at 5 omega speed, but in the opposite direction. Okay. So, there is a fundamental Vr. Okay. Actually the Vr is coincident with Vd. So, this is Vr, it is rotating at omega speed, the d axis is also rotating at omega speed, okay, and the q axis is rotating here. Now, there is a V5 space vector which is rotating at 5 omega speed, but in the opposite direction, and there is a V7 vector, okay, because I have added a fifth harmonic and seventh harmonic to the reference waveforms of Vr. So, V7 is also rotating at omega speed, but again in this anti-clockwise direction. So, if you are an observer, okay, if you are an observer who is standing here and rotating along with the d axis, you are also rotating along with the d axis, what will you see? You will see the seventh harmonic to be rotating at 6 omega speed, because the seventh harmonic is rotating in this direction at 7 omega, and you are also rotating at omega speed. So, this is the d axis where on which you are standing, and then there is a seventh harmonic vector which is also rotating at 7 omega. So, the differential speed between you is 6 omega. What about the fifth harmonic case? So, this is the d axis and this is rotating at omega, and the fifth harmonic, this is the rotating at 5 omega, again the differential speed is 6 omega. Okay. And this is the reason why you see the 6 lobes in the DQ. Okay. So, this is the physical reasoning behind the 6 lobes. Now, it may happen, okay, that this 5 omega, instead of rotating in clockwise direction, it can also rotate in the anti-clockwise direction. 5 omega can rotate in this way also, and in that case you would have seen a 4 omega, which means you would have seen 4 lobes in the DQ in the d axis and q axis, there will be 4 lobes, because if 5 omega, that vector or that harmonic was space vector was rotating at anti-clockwise direction, you would have got a 4 times lobe in it. Therefore, with this understanding of what is physically happening, we can say that these waveforms are obtained Vd, Vq as well as V0. You can take up other cases, unbalanced with harmonics, balanced with non-equal harmonics, and many other things. Okay. And you can yourself see how the alpha, beta and dq transformations, how do you look at it. Okay. So, this here comes the end of the alpha, beta and dq transformation, and this alpha, beta and dq transformation is very useful not only in power electronics, but also in machine analysis. Okay. So, a good understanding of this transformation is essential when you want to go deeper into the subject.